Disseminate, a computer science research podcast.
Hello and welcome to Disseminate, the computer science research podcast. I'm your host, Jack Waudby. This is the podcast where we interview computer science researchers about their latest work, highlighting the problems they've tackled, solutions they've developed, and how their findings can be applied in practice. It's our mission here to help further narrow the gap between research and practice and make computer science research more accessible. So if you are an industry practitioner, researcher, or a student, then this is definitely the podcast for you. You can listen along on Apple, Spotify, all major podcast platforms, and you can now also watch along on YouTube. So if you do enjoy the show, please like, follow, subscribe, do all those things, and tell a friend to help disseminate. In today's show, I was really happy with that joke when I wrote it down. So
Yeah, that's great. That's amazing.
Anyway, cool. So in today's show, we're going to be talking with Navid Eslami about his cutting-edge research on filters, specifically range filters. Navid is doing his PhD in the Systems and Network group, the SysNet group at the University of Toronto, and he recently published a paper on the topic of filters at the Very Large Databases Conference, that's the VLDB conference, and it was titled Diva, Dynamic Range Filter for Variable Length Keys and Queries, which won the Best Research Paper Award. So welcome to the show, Navid, and congratulations on the Best Paper Award.
Thank you so much. It's great to be here.
Cool. Well, let's get stuck straight in then. So let's set some background for the chat. And for those who are new to the area, can you tell us, first of all, what a filter is?
Okay, sure. So if that's okay, I'm going to start with like the sort of killer applications of filters.
Go for it. Yeah, that's great.
Okay. So nowadays, a lot of data systems, particularly database systems, ingest large amounts of data at high rates, right? So this kind of necessitates the databases to support high write throughput. And the way they do this traditionally, or I guess since in the past 20 years, it's been through this data structure called an LSM tree. So at a high level, an LSM tree basically just buffers your insertions into your tables. And once it gets to a specific size that's hefty enough, it's going to write it to disk using very few IOs. But the way this works is whenever it writes to disk, it's going to create a new file that's kind of disparate from everything else that it's written until now. This is great for writes because you don't care where you're writing and you're just buffering everything. But it's not so great if you want to do queries, right? Because then you have to look at every single one of the files and say, okay, does the thing that I'm looking for exist in this file or not? And then search in that. So to get around this issue, people have started using filters over these LSM tree data structures. So what this means is, so what a filter is, it's basically, for each one of these files, the filter is just going to kind of approximate that file in very low memory. So it's a compact probabilistic data structure in a sense that you can give to it a key and ask, does this key exist in that file or not? The filter is going to tell you either it's for sure not going to exist in the file, or it's going to tell you, okay, it exists, but with high probability. It might make a mistake and tell you that it exists even though it doesn't. Okay. The more memory you give the filter, the lower this probability of a mistake is going to go. So that probability is also known as the false positive rate in a sense. So why is this thing nice for something like an LSM tree? It's because if you want to do something like a point query, you want to find like one specific record with a given ID, well, chances are almost all of the files that you're storing on disk aren't going to have anything relevant to that ID, right? So there's only one of them that's going to contain the record that you're looking for. So before accessing each file, if you just ask the filter, hey, does the record with this ID exist in my file or not, then you can avoid accessing most of those files. This is going to speed up your system significantly. And even beyond just database systems, filters have been used in similar contexts for like network applications. You can imagine instead of accessing things on disk, you have some storage medium over the network, and you don't want to do this round trip every single time.
Nice.
So,
cool. Yeah, so it's I always get my false positives and my false negatives around as well. So this is going to be fun for me today because I can always get them the wrong way around.
Yeah,
But
they
yeah,
are
cool.
confusing.
So yeah, so I guess in the example you're using there with the database, I've got some database. I've got a list of all the best sort of all the podcasts in the world, and I want to go and check out his Disseminate in there, right? It's kind of I'm going to ask that query, and it's gonna if it definitely is there, it's gonna say so. I'll either get a yeah, it's there, or I'll get a maybe it's there. Go and check sort of thing. Is that how it's gonna work? But it's never gonna tell me that it's not there when it is there, right? We get no false. This is the question:
Negative.
false, positive, negatives. There we go.
Yeah.
Yeah. Okay, fantastic, cool.
Yeah, exactly. Exactly. Because
Brilliant.
false negatives would result in data loss if you
Yeah,
do that.
and we don't want that.
Yeah, exactly.
Cool. So that's a filter, but your work focuses on an extension of these, I guess, and that range filters. So, yeah, how do we go from filters to range filters? What's the difference there?
Yeah, sure. So it's so range filters are in a sense a really natural extension of filters, because filters traditionally only support queries with a single key, right? So the question is, okay, I have my database, and well, a lot of my queries are actually ranges. I want to scan all the pieces of data that are within a given range. I can't really use a standard filter to do this because it doesn't give me the relevant API. So the question is, can I have a range? Can I have a filter or a range filter that I can give it a range and ask, is there anything included within this range or not in my file? So then if you just have this data structure, now suddenly you can do range queries over your LSM tree as well as the point queries you were doing before.
Nice, cool. Could you maybe give an example of I don't know, of what a fun example might be of such an application that would do such range queries?
Yeah, sure. So I guess one standard example might be, let's say if you have a database of patients and you want to just find the patients that have an age between, let's say, 50 and 60. So that your range would just be 50 to 60, and you're looking for your keys are the integers between these two numbers. So you just
Nice.
want to filter those out.
Cool. So that sets us up nicely then for the sales pitch for Diva, I guess then. So yeah, what's the TLDR on it, the overall elevator pitch for it? How how would you probably explain it to your grandma, I guess, as well, sort of if you sort of summarizing up the whole piece of research in one go.
Sure. So at a high level, what Diva does is basically it lets you do range filtering with theoretical guarantees. So it's going to give you a provable false positive rate that also works on string keys, so not necessarily only integers. And it doesn't impose any restrictions on the kinds of queries you can feed to it. So the query can be like extremely big, the range, or it can be really small. That's the high level pitch.
Nice, that's cool. So yeah, let's dig into then. So how did you arrive at this research topic, I guess, and kind of what was the specific gap or question you were setting out to answer?
Okay. So we were basically looking at the existing range filters, and we saw that, okay, almost all of them, well, almost none of them give you a nice false positive rate guarantee. So they use some amount of memory, but it's the filtering that they give you doesn't necessarily correlate with the amount of memory you give to the filter. So it might not give you the best possible false positive rate given that memory budget you give it. So the second issue is the filters that do actually give you a false positive rate guarantee, they don't really support range queries that are too big. Because if you issue a range query that's really big to those types of filters, what's going to happen is their false positive rate is going to go all the way up to 1, which means that any query you give it, it's always going to return, yes, it exists, which is going to make it practically useless. In addition to that, sometimes the performance of these filters also gets really, really bad when you give them a long range query. And so much so that it's like on the same level as doing an IO, which is not great. So that's the second problem. The third problem is that almost none of these filters support variable length keys, meaning that they only operate over integers, let's say. The only one that does support variable length keys does not give you any sort of guarantee on the false positive rate it gives you. Okay. And the fourth issue we saw, which was that, okay, all of these filters are kind of like static structures. You can't really do insertions and deletions to them. So except for one, which was actually our own work prior to Diva, that was like the first range filter that supported insertions, deletions, and it could accommodate workloads of growing size, so it could expand itself. But yeah, none of the other filters achieve this. And you can see that I have these 4 criteria that I want to achieve, and I want to achieve them with high performance. So in some sense, I have 5 goals. And what's interesting is that, okay, of these 5 goals, 2 of them are kind of non-existent among the current filters. And for sure, none of the current filters give you these 5 at the same time. So we thought, okay, let's try and do this and give the people kind of like the holy grail of filters.
Nice, yeah, that's what I was thinking about. Like, you get all these 5 things. That's all the 5 special ingredients to make some, really good sauce there. So yeah, just to recap really quick. So there's nothing out there that sort of give any sort of guarantees of the false positive rate. The ranges were often too big, or if they got too big, basically it kind of got redundant because it went to 1. So basically, there's no one that could kind of handle variable size or large ranges. Integer keys only, which again feels an incredibly restrictive API, right? Like kind of, I imagine a lot of use cases or a lot of data kind of have strings as keys. So yeah, that feels okay. Would be nice to have that. And lastly, static structures, right? So yeah, data is dynamic, right? So people want to insert and delete things. I mean, it's often, I guess, it's a assumption in a lot of research works. Oh yeah, just assume things are static because it simplifies the game a little bit, right? But yeah, in reality, things are dynamic, right? So yeah. And we want to do that as fast as possible, right? And achieve all of these goals while being really high performance. So yeah, so that was the goal then. So I guess maybe now should we talk a little bit? We kind of covered off there kind of what the existing solutions are like and how they perform and where they fall short. So maybe we don't need to go into those in too much depth then. So let's switch on to Diva then and talk about how you went about achieving the Holy Grail.
Right. Okay. So this whole story with Diva started from this theorem from the theory community back in 2014. So it's basically, the theorem is quantifying you how, like, if you want to have a range filter that guarantees a given false positive rate, how much memory you need to use. And if you look at it, you'll see that, okay, if I want to support string keys, the theorem is basically telling me I have to store the actual keys. There's nothing interesting I can do. Okay? So in some sense, when you hear this statement, you feel like, okay, the problem is kind of intractable. I can't really do much here. Well, then we looked at it and we saw that, okay, this theorem is actually only talking about the worst case scenario, which doesn't seem to be that common in reality. So we thought to ourselves, okay, what can we say about the common case that we do see in reality and in practice? Maybe we can do better for those. And that brought us to this assumption of, okay, well, most of the time, our data follows some nice distribution. So maybe if we assume that our data comes from this nice, smooth distribution, then we could do better filtering better. So that's kind of like the starting point. We wanted to bypass this theorem or this lower bound to achieve space efficiency while
just going to ignore the theorem committee. By the way, the theorem committee sound really kind of a cool sort of I don't know, quite a scary group of people. The theorem committee, I don't know, yeah.
It's the people in theory of computer science.
Cool. Sorry, I continued. I interrupted.
No, that's okay. Yeah. But yeah, I guess we had this observation, and we thought, okay, let's suppose our data has a distribution. And kind of the first step we took after making this assumption was, okay, so I want to leverage this distribution somehow. So what I do is I take some samples from this distribution to kind of get an idea what the distribution looks like and learn it in a sense. And that's basically just this corresponds to saying that, okay, if I have a data set with some number of keys, I'm just going to take like every 1,000th key. That's going to be my sample set. This is going to give me a really good idea of what the distribution looks like. And based on that, I can do some more interesting things. In particular, if your distribution is smooth enough, let's say, in between each two samples you pick, you're going to have an almost uniform distribution. If you look at like the distribution function, in between each two samples, there's going to be like an almost straight line connecting them. That corresponds to an almost uniform distribution. So this means that the keys that you kind of emitted between these samples were almost uniformly distributed. So we're going to leverage this property to give you a really space-efficient encoding of the keys in your set. So the way we would do this is, well, we're first going to store the samples that we picked out in some data structure. Let's say it's just the binary search tree. In our work, we use something known as a Y-fast-try. This is like a cute data structure from the 80s, but that's besides the point. It just gives you like a slightly faster lookup time than just the binary search tree. Well, let's say we have a binary search tree over our samples. Now, this gives me access to that nice approximation of the distribution. Then what I do for the keys in between any two consecutive samples, because I know they're uniform, I can lossily compress them and store them in these data structures we like to call infix stores. So the compression, the way it goes is any two consecutive samples I take, well, these two samples have the longest common prefix, right? Any key that I take in between these two samples in lexicographic order is also going to have the same longest common prefix. Okay? So because I'm already storing that longest common prefix in my binary search tree, I don't have to store it in these infix stores too. So I can just remove that longest common prefix. From what's left of each key, then I can take like a small patch of bits at the middle that kind of differentiates between the keys that are in between the two samples. And because I had this uniformity property, that small patch of bits, which we call an infix because it's in the middle of the key, that small patch is going to be almost uniformly distributed. It's going to inherit the uniformity of the key itself. So I have kind of like a small summary of the key, which, well, it's part of the key itself, so it's order preserving, and it's almost uniform. Okay? So in some sense, the uniformity kind of makes it look like a hash of the key, because that's what a hash is in reality. It's like a small summary of the key that looks really random. In our case, it also looks random, but the additional benefit is that it's actually order preserving. So we summarize these keys in between the samples as these infixes. And we're going to leverage this hash-like property of the infixes to store them in something that looks like a hash table. So the way this is going to go is each infix, we're going to split it into an address and a remainder, is what we like to call it. This procedure is known as quotienting in a sense. The address is telling you where in the hash table you want to store the infix. And in that position, you're going to store the remainder. So what you get in the end is a order preserving hash table that, it's an order preserving hash table that gives you constant time access to the infixes in between two samples.
Nice, cool. So once we've got this data structure, can you walk us through kind of how we go the other way then? So kind of, I think it'd be quite nice to go through how a range query works on top of this then.
Sure, of course. So a range query is actually really simple to handle with this structure. So you had this binary search tree, right? And then in between each two consecutive samples, I'm assuming that the samples are ordered lexicographically, right? Mm-hmm. In between each two consecutive samples, I have a small infix store, right? So the way a range query would go is I have my range. I'm first going to look at this binary search tree that I have. And I'm going to check if there's any key that is included within my range, right? Because my binary search tree is storing the actual samples themselves without any loss, I can do this check exactly. And if I find something that's in the range, well, the answer to my query is a true positive. So I just return that and I'm happy. So in some sense, the interesting case is when I don't have any samples within my range. In that case, well, if you think about it, you'll see that, okay, this means that the endpoints of the range query are both in between two consecutive samples, because otherwise they would have contained some sample. So this means that, in other words, this means that the endpoints of the range query are fully included within a particular infix store, right? So then what you do is, okay, you take the endpoints of the query, you kind of do the same compression algorithm that we did for the keys in between the two samples to convert these endpoints into endpoint infixes. Right? And then look at the order preserving hash table to see if there's anything in between these two endpoint infixes. If we find something, the answer is the query is a positive. And if we don't, the query is a negative. We get false positives because this compression scheme of removing like the longest one prefix and just removing some other suffix to get the infix, this is lossy. So there is some chance that you might accidentally match something that wasn't exactly the key you were hoping for.
Nice, cool. So this, as you've been talking through this example, then I'm thinking, okay, I can see how this is all constructed and works nicely for static data. How do we then go and make this dynamic? Like, how do we then handle inserts, deletes, and expansions as well? And kind of what are expansions? I want to ask as well. While I saw that mentioned in the paper, like expansions. What do they mean?
Sure. So let me start with how you can do inserts and deletes. Then I'll get to expansions.
Yeah.
Okay. So inserts and deletes are quite straightforward. Well, they're not straightforward in some sense.
They're straightforward for you, Navid. That's it. Yeah.
Right. So inserts and deletes, the way they work is, okay, let's say you get an insert, right? What Diva does is when it sees the new key, it's gonna flip a coin. With some probability, it's gonna take that new key to be a sample. So it's gonna insert it into the binary search tree of samples that we had. If it does this, then this means that it kind of lands into an infix store, and it has to split the infix store into two halves, right? So now you're kind of like, this is sort of similar to how a B tree works, if you're familiar with it. So you like insert a new thing, and it splits like the infix store into two halves, which is just like a smaller subset of the problem. So that's one scenario if my coin tells me to insert it as a sample. The other scenario is my coin tells me to not insert it as a sample. So this means that I just go to the relevant infix store for that key, and I just insert it as an infix. Really simple. And deletions are kind of the same. You follow the same procedure. Well, you don't have the coin flip anymore. But if you find a sample within your tree that matches your deletion, then you just remove that and merge the two infix stores. But if you don't find the sample, then you just go to the relevant infix store and find an infix that matches your key to the best amount in some sense, and you remove that infix that matches it the most.
Nice, cool, yeah. And expansions.
Right. So expansions. So an expansion is basically just a fancy word for saying that I want my data structure to resize itself as I insert more stuff. So you can imagine in the insertion procedure that I mentioned, because I'm doing this coin flip procedure, there is a chance that for a long time, I don't insert any samples. So I'm going to have an infix store that's kind of big. It's going to get full, right? So I have to reallocate it in some sense and give it more memory so that it can store the extra data. That reallocation process is known as expansion. And the cute thing that we do in Diva that's sort of different from how other filters do expansion is, other filters do this, I guess, classic procedure of expanding by doubling the size of the array and then inserting your new keys. We do it by expanding it in fractionally, in some sense. We increase it by a little bit so that you don't have this wasted space by doubling. Because if you double, then there is a chance that half of the space that you're using for your filter is going to be empty, which is not great for something that's supposed to be really space efficient.
Yeah. Cool. I guess now might be quite a nice time to then talk about evaluation and results and how well Diva performs. So I guess the first thing would be to ask, how did you go about evaluating Diva? What was the setup looking like? who are you comparing it against? And yeah, so let's take that question first, then we can give us some clickbaity results that we can chop up and make some shorts out of. Yeah.
Right. Awesome. Okay. So the overall setup is we do both micro benchmarks and a integration benchmark. For the integration, we're integrating the range filters that are integrable in some sense into WiredTiger, which is sort of like the back end of MongoDB. Yeah. So let me start with the micro benchmarks. For these benchmarks, we are comparing against pretty much every single range filter that's out there. The ones that are important to note, I think, are Surf. Surf is like the first range filter that was designed. This is the only range filter that supports string keys, variable length keys. And Memento, which is our previous work. This is the only range filter that supports dynamic updates. Okay, so when compared to the other range filters, in general, Diva gives you like almost the best false positive rate. Like it's better than, actually it gives you the best false positive rate that's stable with the range query size. So no matter what range query size you feed it, it's always going to give you a really stable and constant false positive rate that's better than anything else that you can see. There are like one or two filters that are slightly better than Diva in terms of the false positive rate. Well, those guys are actually much slower in terms of query time, and they're not updatable. So you can't do any inserts and deletes to them. So that's like the setup against ranges of different size. If you care about string keys, well, then the only range filter that's relevant is Surf. Compared to Surf, Diva gives you like 1 to 2 orders of magnitude better false positive rate at the same memory budget. Yeah, so that's like the benefit you would get, and it's really much faster than Surf. Because Surf is like, yeah. Anyhow, it is much faster.
How much faster is it then? Give us some numbers.
So it kind of depends on the type of data that you're working with, but in theory, what can happen is Surf, morally speaking, Surf is like a trie. So it has to like go down this multi-level trie and the number of levels that are in the trie is basically the length of the strings in your workload. So that means for each level of the trie, you're going to incur a single cache miss, which is going to scale pretty poorly in the length of the key. Diva, in comparison, because it's using like the Y-fast trie thingy, it's going to take actually logarithmic time in terms of the length of the key. So it's exponentially faster in some sense than Surf.
Nice, cool. Yeah. Do you want to talk about? Should we talk about the white? So I'll let you continue, Navid. Sorry, I interrupted.
Yeah, there is one more thing that I want to
keep going. Yeah, keep going, man. Yeah.
Yeah. So yes. So against Memento filter as well, which is the only other dynamic one. Well, both Diva and Memento can expand. So when compared to each other, you'll see that okay. Performance-wise, Memento filter is a little bit faster. Well, yeah, it's like faster by 1.5x, I think, if I recall correctly. And the reason for that is, well, because it doesn't have this extra binary search tree that it has to go through to get to where it's supposed to go. It's just using hashing. But even though it's slightly faster, it's much worse in terms of false positive rate when you do long range queries, even as you're expanding the data set.
Before we talk about the WiredTiger implementation, I'm very intrigued about that. How does the performance how is the performance affected by the kind of proportion of inserts and deletes going on as well? Like how does what's the relationship between the I guess the writes and the reads, I guess?
Right. So they don't really impact each other that much. Okay. Because the scaling, yeah. If you were using a normal binary search tree in Diva, then they would impact each other, because then with more inserts, you're gonna get the binary search tree is gonna get bigger, and you're gonna be slower in your search.
Yeah.
But the Y-fast trie actually gives you a access time that's independent of the number of keys.
Okay, very nice. With. Yeah.
So in that sense, they're both constant.
Yeah, very nice property. Cool. So let's talk WiredTiger then. So first of all, tell us a little bit about the implementation of and how easy it was to implement it in WiredTiger, and then tell us how how it improves what was already existing in WiredTiger as well?
Yeah, sure. So the implementation itself was actually very easy because we give you like a really nice header-only implementation of Diva, which you can just plug and play. And we just had to place it on top of the interface for accessing like the B tree and WiredTiger. So before accessing, so again, WiredTiger is like a key value store that's formed as a B tree. Just before accessing the B tree to get your desired record, you just have to ask Diva first to see if it exists. If it exists, it tells you go access the B tree, and if it doesn't, it tells you don't bother. Right? So it was really easy to integrate it. We just put Diva as like an upper layer over WiredTiger. And compared to the things that existed beforehand, well, Memento filter was really the only other range filter that I don't know was integrable with WiredTiger, because you have this dynamic database which you're doing inserts and deletes to. So the filter that you're using must also be dynamic. You must also support inserts and deletes. So really the only other filter that fit bill was Memento. Compared to that, well, if the workload was similar, Diva actually achieved the same. Yeah, if you were working over integer keys and you didn't have long range queries, let's say, Diva achieved the same false positive rate as Memento, and it gave you pretty much the same performance. This is because then when you're using a database system, the bottleneck really comes from, well, most of the time, it comes from the disk accesses you're doing, not the filter time itself. But I guess the core benefit is that now you can also do string keys, which Memento filter doesn't even work with. Or if you have long range queries, which Memento filter can potentially be extended to support, Memento is going to get a really bad false positive rate, which is going to translate into a very slow system, which is just going to do redundant accesses to disk. Whereas Diva is going to let you, filter everything out, irrespective of the range size.
Nice, cool. So for all our listeners who have always wanted to do range queries over variable length keys but haven't been able to now, is Diva actually available to like users of MongoDB? Can they actually use Diva, or is it publicly available? I guess is what I'm asking.
Yeah, of course. Diva is open source, so you can just go to my GitHub page and pick it up. It is. I tried to make it as user-friendly as possible. It's just a header-only file. You include it, plug and play. You just do your workloads, and you're happy. It is also thread safe. Actually, that's a new addition. So if you have a multi-threaded system, you should be happy with that as well.
Fantastic. We'll put a link to that in the notes so the interested listener can go and have a play. So let's change gears a little bit now and talk about surprises. So whilst you were working on the project and with range filters on Diva, was there any sort of thing that sprung up, any sort of counterintuitive findings or results that really sort of challenged your initial assumptions about range filters?
Yeah, for sure there were. So the biggest one was when we started this project, we had this conception that basically every single workload with variable length keys had a smooth distribution. In particular, like natural language, we assumed had a smooth distribution. But when we got into evaluating it, actually, we saw that, okay, there are some specific natural language data sets that don't seem to be as nice in terms of the distribution. They're not as smooth as you would expect. For those, it actually turns out that both Diva and Surf, if you just use them as is on these data sets, you're not going to get a great false positive rate. But we also observed that, okay, the reason why we are getting a bad false positive rate on these data sets is actually because there's a lot of redundancy in the English language, in the sense that there are specific combinations of characters and words that are really common. And if you think about it, okay, because the way I'm deriving the infixes is I'm just removing the longest long prefix and I'm taking some bits. That redundancy is going to translate into the infix that I take at the very end. So what that's going to do is it's going to make the infixes less suitable for differentiating the keys. in some sense, and that's going to mess with the false positive ring. So where am I going with this? I'm saying that I have this redundancy that's causing me issues. So why not do some compression algorithm to remove the redundancy? And it turns out we did a order preserving compression of the keys. And it turns out when you do that, the distribution of the keys in your workload are going to get much smoother, and you can use Diva over that newly modified dataset.
Nice. That's a good segue into limitations, because I was going to kind of ask you about this assumption of having a smooth data distribution there, and saying, well, how likely is that in reality? How often do we see that? But it's you can actually often, with like the technique you just mentioned there with compression, actually take something that isn't smooth and kind of make it smooth, right? But yeah, I guess the question that still stands is then, are there any limitations, any scenarios in which I shouldn't be using Diva, or Diva still can be improved maybe in certain places?
Yeah. Okay. So the core limitation that is, as you mentioned, if you have a non-smooth distribution, you have to do some pre-processing in some sense to make it smooth. That, I think, is like an open research question in some sense. We have to study it a bit more to see what type of pre-processing we have to apply that best smooths out the distribution. There is also another limitation in the sense that, okay, you might have your range queries might be constructed in such a way that you care about some range that's really close by to a given key. Okay. So you can imagine you have a key that's, let's say, 1,000, and your range is from 1,001 to 1,002. So it's like really close to the key, but it doesn't include it. Okay. This type of a workload, we call it the correlated workload in the literature. For this one, Diva, because of the way it only takes the infix and it throws away like the lower order bits of the keys, is not really able to help you in filtering these types of queries out. But the thing is, this is kind of a philosophical point. If the ranges that you care about are really similar to the keys, that in some sense kind of implies that you know a lot about your data set. And if you know a lot about your data set, then it's kind of questionable that you want to issue range queries that are kind of empty. And you know what the data set is, so why not just iterate over the stuff that you know exists? So in some sense, this workload that I mentioned, this correlated workload, may or may not be really something that you see in practice. To me, it seems like the most reasonable scenario where you would use a range filter is when you don't know a lot about the data set. So the range queries you issue are likely to be empty. In that scenario, Diva is perfectly fine. You could use it. But if for some reason you happen to know a lot about your data set and you want to like issue this range query that's really close by to a key, it's not going to help you there. You have to use something similar to Memento to filter those out. And by the way, this is like the worst case scenario that the lower bound that I mentioned, the theorem that I mentioned, is kind of exploiting. So in some sense, you can't really do better than the memory usage of Memento to handle these.
Do you feel like if you can have both like Memento and Diva in the same system, you like would you have it? I don't know how you would basically have it. I'm sort of like, can both coexist in the same system, and depending on your query, you can use one or the other, right? And have that. And I don't know whether the selection of that would need to be sort of human driven, or you can have some sort of, I don't know, optimizer or something that can say, okay, you should probably use this one or use this one, essentially. Anything like that where they can coexist?
I think so, yeah. I think like the simplest solution might be to just put a threshold on the size of the range. If it's smaller than something, use Memento. If it's bigger than something, use Diva.
Sure, some simple heuristic like that, or that would work.
Yeah, I think, there's, and I actually think that I thought about this problem for a while, and I actually don't think you can do better memory-wise than just having a separate Memento instance and a separate Diva instance and use them together. That seems to be like the optimal you can achieve.
Nice, cool. I guess then, where do you go next with Diva? Though, where's the future what's the future hold for it?
Yeah, that's a good question. I think the main thing that we should research in the future is how you can smooth out non-smooth distributions. That's like the biggest thing you can, in my opinion, you can work on. I am actually working on some techniques to address that. So hopefully we'll get that out at some point.
So just on, like you said, the very fertile area for research is finding out how we can take data sets and make them smooth. Do you have a sort of a handle on out in the wild how unsmooth data actually is, or is it just so application sensitive or like context dependent where it's kind of really hard to say?
Well, most people that I've talked to that are actually interested in using range filters seem to have data that is quite smooth. I'm not entirely sure about like the average workload across all industries, of course.
Yeah.
But the people that I've talked to seem to have smooth distributions mostly.
Okay.
And it seems to me like when I think about this problem, it seems to me, oh, okay, usually your keys are like maybe names, natural language, but perhaps, or like email addresses. Those seem to me to be non-smooth, but they're very structured, and the structure is very well understood. So we should be able to do some nice compression to make them work as well. So I don't think it's that bad, but of course you can have like a weird composite key that's not smooth. So that's completely domain specific. You have to do like a specific compression for that.
Yeah, some adversarial case. Yeah, they always exist, right? Cool.
Yeah.
So let's talk about impact then and practical relevance. And so, my first question is, I guess, how much impact have you seen Diva have so far since it was published?
Right. So it is a little bit early, I think, for us to see some impact. But I have seen a lot of interest, and we are actually in talks with some companies about integrating Diva into their systems. I'm hoping to see Diva show up in a lot of systems, mainly because this LSM tree structure that I mentioned is like the killer application for a range filter, and it's extremely widely used across the industry. Like one really famous example is like in RocksDB. You can just plug Diva into RocksDB and you get all of the benefits out of the box. Yeah, and we do actually have an internal project in the University of Toronto that does this, but it's not published yet. So it's like internal
Watch this
knowledge
space.
for you.
Yeah.
Yes.
Cool. Sweet. So I guess that brings us nicely on to the last word then, Navid, and there's two things here. The first of all is what should practitioners take away from this work, and secondly, what should researchers take away from this work and your the podcast?
Right. So for practitioners, I think the nice message is that you can actually have data structures and I guess techniques that are grounded in theory that give you really nice guarantees that are also useful in practice. I think that instead of, well, I mean, going to heuristics to implement a whatever data structure you want for your system is a fine choice, and it's oftentimes the correct choice given the time budget you have. But if you really want something that's never going to break under any circumstances, it is possible to. I believe that it's possible to design structures that give you strong guarantees like that. Diva is one example of that. I think I would like to encourage the practitioners to think about this a bit more, maybe like consider having structures that give them strong guarantees so that they don't have to deal with the headaches of things breaking later on.
Nice.
That's for the practitioners. For the researchers, I think the nice message I have to give is, again, tied back to the lower bound that I mentioned at the beginning. The statement of the lower bound kind of seemed pessimistic, right? It seemed like you couldn't do anything good in this space and everything was done, so why even bother? But oftentimes, maybe not oftentimes, but a lot of the time, when you look at these lower bounds, you see that they're actually leveraging properties of the problem that are really hard, and they only appear in the worst case. In reality, a lot of people don't deal with those worst cases. So I would actually encourage people to think about what properties we have of the data we care about in practice that can help us in designing these types of structures. Like it could be an algorithm, it could be a data structure. In designing any one of these, I think it's nice to find those specific properties and kind of tie the algorithm to that property to get like a better performance out of the entire thing. So this gives you like a broader spectrum of problems you can work on if you go beyond this worst case in some sense.
Nice. Yeah, it's a great message to end on there, Navid. So, but one last question, actually. I said that was the last word, but I've got one last question. Diva, you need to tell us about the name because naming's important. Why is it called Diva?
Yeah, that's like it's like a weird acronym I came up with on the spot.
Right.
So Diva, the D and the I come from dynamic. If you look at the title of the paper, the D is from dynamic and the I is from the end of the word, and Va is just for variable length. So we
Okay.
just like concatenated these and got Diva out.
Yeah, and it's a bit of a diva as well. It's pretty cool, right? So yeah, it's got that going for it as well. Great stuff. Great. Well,
Yes.
we'll end things there then. That's great. We'll put links to everything you mentioned in the show notes as well, so the listeners can go and connect with you. Are you on social media anywhere? Where's best to find you?
Yeah, that's a good question. I'm not actually on social media.
Yeah, we maybe like the homepage or something. We can link maybe. So yeah, we can drop that in there.
Yeah,
And
I do have a GitHub page. So if you're interested in contacting me, please check that out. I will answer emails, and yeah, I'd be happy to chat.
great stuff. Yeah, and go play with Diva. That's the last thing we want to say.
Yes,
Cool.
yes, please do.
Great stuff. Thank you very much.